In this video, we're going to derive the distance formula for 2 points in three-dimensional space. To make this derivation easier, we're going to draw our first point as if it's in the floor, as if it's in the XY plane. It'll just make it a little easier to visualize. However, we are going to let this Z coordinate be Z1, indicating that it could actually be anything. It does not have to be Z is equal to 0. And then we're looking at another point somewhere out here. We'll call this one P2, where the X, Y, and Z coordinates are the second points that we're looking at. And our goal is to determine the length of the line segment that connects these two ordered triples. So the first thing that we'll do is we are going to drop a perpendicular from the second point down to the same horizontal plane. Again, we're drawing it as if it's in this XY plane or in the floor here. But that's just for the ease of drawing it. And when we draw this, dropping that perpendicular down, we're going to end up with a third ordered triple. Now, this ordered triple is going to share some values with P1 and P2. Namely, first of all, we're going to have the same x coordinate as we had with P2. So that's going to be, we'll write that as being x2. We're also going to have the same y coordinate as P2 does, so we'll say that the y coordinate is going to be y2. And since we're coming down to that same horizontal plane as P1, we're going to share the same z coordinate as our first ordered triple. So now we get to draw a box, and we're going to come on out to this first order triple so that we have a box in that floor, and then as well we'll come up from this point here to make the back wall of our box, and then here's our side wall of our box, and so on. So now the distance that we're looking for goes from this front left corner of this box through the center of the box to the back right corner of the box. And we're actually going to go ahead and make a right triangle so that the distance that we're looking for is the hypotenuse side of this right triangle that pretty much slices right through the center of this box. Now we can use some of the formulas that we know from algebra. Let's look at the distance from P1 to P3 here. And since we have it drawn as if it's in the XY plane, we can use our two-dimensional distance formula because there's no change in the z value. It's as if we are looking in the XY plane. Again, we're just drawing it in the floor for the ease of this derivation, but even if it were in a different z plane, there would be no change in z, so we can still use our two-dimensional distance formula. So let's look at the distance between point 1 and point 3, and we'll say that's going to be equal to the square root of the P3x coordinate is x2 minus the P1x coordinate is x1, and then we're going to square that, plus the P3y coordinate is y2 minus the P1y coordinate, which is y1, and there is no change in the z value. Even if we did think about that as z1 minus z1, that would zero out. But like we said, we're just using that two-dimensional distance formula. Now let's also think about the distance between the P2 point and the P3 point, right? So this vertical leg, we've already represented this horizontal leg over here. So we're looking at the distance now between P2 and P3. And because the x values and the y values are exactly the same, this distance here is going to be simply a change in the z values, right? And when we're looking at a change in z, we're thinking about, we can say this by z2 minus z1 or terminal minus initial to get that distance or that change in z. But because this can be anywhere and it's not necessarily having to be in the first octant, we do want to wrap this in abs-val bars to ensure that that change in z is a positive value, to ensure that that vertical leg is a positive quantity. So let's say this is going to be z2 minus z1 in abs-vals. Now let's recall that by the Pythagorean theorem, the length of side P1 to P3 quantity squared plus the length of side P2 to P3 quantity squared is going to be equal to the distance that we're after squared. So our distance squared is going to be the P1 to P3 side squared. So if we square this quantity, it just gets rid of that radical. So we would end up with just x2 minus x1 quantity squared plus y2 minus y1 quantity squared. And then when we add P2 to P3 quantity squared, then we're basically going to be squaring this. And when we square this difference, we no longer need these abs vowels. Now we can just look at z2 minus z1, because whether that's positive or negative, when we square it, we get a positive quantity. So we don't need the absolute values to ensure that it's positive anymore. So now we're just going to say z2 minus z1 quantity squared. And then to solve for this distance, we just take the square root of both sides. So our distance formula in three-dimensional space is just going to be exactly kind of what we were hoping it would be, which is x2 minus x1 quantity squared plus y2 minus y1 quantity squared, which is our 2D distance formula. And then all we have to do for the 3D distance formula is add on z2 minus z1 quantity squared, and there we have it.